The purpose of this lab was to model an elastic collision while using Newton's second law and the momentum principle. A Python code was created to track the total momentum of the system before, during, and after the collision. It was concluded that the motion could correctly be modeled through Python while satisfying the principles of an elastic collision. The experimental setup was modeled by two toy cars. The first car started with a constant initial velocity, hitting the second car and causing an elastic collision. The video was then uploaded into Tracker, and the position of the two cars was tracked. The coordinate system was set with the positive y direction pointing up, the positive x direction pointing right, and the origin set in the center of the blue car on the right. Then the average position of the cars at each time interval was plotted. After the collision happens, the blue car comes to a stop and has zero velocity. Before the Python code was created, it was imperative to find the speed of the first car before the collision. The equation used to do this was delta x over delta t equals v. It was found the velocity of the blue car before the collision was negative 0.25 meters per second because it moves in the negative x direction. Other equations that were important for this lab were Newton's second law, which states that the change in velocity is equal to the net force divided by the mass times the change in time. Then the position equation, which states that the change in position is equal to the velocity times the change in time. And the momentum equation, which states that momentum is equal to the mass times the velocity. It is important to note the qualities of an elastic collision. In an elastic collision, the kinetic energy before the collision is equal to the kinetic energy after the collision. As well, momentum is conserved throughout the interaction. Next, these principles were applied to a Python code. First, the initial conditions were set to mirror those of the experiment. The mass of the cars was 0.034 kilograms. The blue car started at the origin, moving in the negative x direction at a speed of 0.25 meters per second. The blue car started at rest at negative 0.201 meters in the x direction, as shown in the information given in Tracker. The first while loop models the motion of the blue car before the collision. Newton's second law was used, and then the momentum and kinetic energy was calculated throughout the while loop using the equations shown previously. Because the car is moving at a constant velocity, the net force is zero, and the momentum of the car will stay the same. By calculating the momentum and kinetic energy before and after the collision, we can see whether the kinetic energy and momentum is conserved or not. Next, the interaction during the collision was modeled. The net force acts in the negative direction on the red car. This force is important to the red car because after the collision, the blue car comes to a stop. Therefore, the momentum of the system completely transfers to the red car. By using Newton's second law during this time interval, the net force of the collision could be found. Because the blue car comes to rest after the collision, the final velocity is zero. After the calculations, the net force was found to be 0.25 newtons. The code after the collision looks almost identical to the code before the collision, except the momentum and kinetic energy is dependent on the blue car and not the red. Running the code, the interaction plays out similar to what was shown in the video. The momentum of the system was tracked in the graph before the collision. The momentum was higher. Next, I compared the values I obtained in Tracker to the values I calculated using the data from Tracker. The final momentum, kinetic energy, and velocity of the red car are slightly less in the computational model than the experimental model, but they are still very close. This discrepancy can be attributed to the fact that the force of the car was not completely constant the entire time they were in contact. Therefore, their values of the velocity and position would be slightly different in the computational model than the experimental. Although the numbers are slightly different in the computational models, the value in the experimental model do satisfy the conditions of an elastic collision. Through this experiment, it was determined that an elastic collision could be successfully modeled using Newton's second law and the momentum principle in relation to the qualities of an elastic collision.